Good morning, everybody. And my name is Xiguang Wang. I'm an assistant professor from School of Meteorology, University of Oklahoma. It's my great pleasure to give this invited talk on the hybrid ensemble-variational data simulation for numerical weather prediction. Can you hear me well in the back? Okay. Next. Who is going to? Okay. All right. So I have been working on the hybrid data simulation for almost 9 years. Looking back, the history of hybrid data simulation to me is a very nice example of transitioning research to operations. So it started from the initial theoretical development, and then basic research with simple model and simulated data, and then system development for real NWP models and real data, and ultimately the operational implementation at operational NWP centers. Here I just list two examples about hybrid data simulation systems. One is warfare hybrid system. The other is the GSI hybrid system. GSI is the U.S. operational data simulation system for both the global and the regional forecasts. And over the past 2 years, through the multi-institutional collaborations, significant efforts were conducted to develop the GSI hybrid system and test the system with the Ensembl operational global forecast system, GFS. And the hybrid system showed significant improvement, as I will share later. And this system became operational about 6 months ago on May 22nd for the global forecast system at Ensembl. On the other hand, efforts are being conducted to further test the system for the regional forecast system like the HWRF, Warfare W, and the Rapid Refresh. And the hybrid system is becoming the method of choice of many operational centers in the world. So first, I will talk about what is hybrid and why we want to have a hybrid system, and I will show pre-operational test results for the GSI hybrid for the GFS, including both the 3D hybrid and also the 4D extension. There are many efforts in testing the regional system using the hybrid system, but due to the time constraint, I will only show one of our most recent efforts using the GSI hybrid integrated with the operational hurricane WRF and test that with the airborne radar data simulation for one hurricane case. Before the emergence of the hybrid system, there were two parallel data simulation frameworks. One is the variational method. It's very popular for operation centers. It involves a single forecast analysis of forecast cycle. Next. Another one is ensemble common filter. It involves multiple forecast analysis and forecast cycles. And hybrid is a combination of the two. So for one-way coupled system, we just incorporate ensemble covariance into the variational system. Next. For two-way coupled system, we further recenter the NCAR analysis on the control analysis output from the VAR. Next. So this flowchart actually applies for both warfare hybrid system and also the GSI hybrid system. Next, please. One of the important components in the hybrid is how to incorporate the ensemble into the variational system. For both the warfare hybrid and GSI hybrid, we use extended control variable method. But I'm not going to go through the math today because it's very complicated. But if you're interested, we can talk offline, or you can also refer to these references. Next. So the big question is, why do we want to have a hybrid system? The answer is we really want to try to take advantages of best aspects from both the VAR system and the NCAR. So relative to a pure VAR system, the hybrid system can benefit from the flow-dependent ensemble covariance. For a typical VAR system, it still can be limited by the use of static covariance. So relative to a pure NCAR system, the hybrid can also have some advantages. For example, our early studies suggest that if we can only afford to run a small number of ensemble members, the hybrid can be more robust. And there are other studies suggest that the hybrid can be better in the simulation of satellite radiance data because the better localization for integrated observations. And there are also studies suggest that because the hybrid system is still using the variational framework, so the hybrid can benefit from the dynamical or physical constraints, while the NCAR is purely statistical-based method. Because the hybrid is also based on the existing variational system, it can take advantage of many existing capabilities like the variational QC or auto loops. Here, I just give you two idealized examples to illustrate what's the difference between the static and flow-dependent covariances. The first case is a warm front, and the second case is a tropical cyclone. In both cases, we just simulate one single observation. For the middle column, you can see that for the 3D VAR using static covariance, the correction made is basically centered around observations locally. For the ensemble-based method, you can see for the first one, the increment is actually parallel to the isotherms of the warm front. And for this tropical cyclone case, it's actually, the increment is actually surrounding the TC center, suggesting a stronger TC vortex. So it's highly flow-dependent. Another difference between static and ensemble covariance is the cross-variable update. For example, this is Hurricane Ike 2008. We use OFR hybrid to simulate radial velocity data from two ground-based radars. For the first row is the wind increment. You can see for both radar and hybrid, it suggests a stronger TC vortex. But they are very different for temperature increments at lower levels. For example, although the wind increment suggests a stronger TC, at lower levels, the 3D VAR actually give a negative or cold increment at the center of the TC, which is not consistent. For the hybrid, it shows a warm increment at the center, and the increment is also following a spiral ring band structure, which we normally would understand what the TC should look like. Relative to the pure NCAP, the hybrid can be robust for small ensemble. For example, our early studies suggest that, for example, 15-member, the well-tuned hybrid and the NCAP, they can perform very similarly. But if we reduce the ensemble size from 50 to 5, the NCAP can experience filter divergence, but the hybrid can still be better than the one using just the static covariance. And the hybrid can also benefit from the variational constraints. This is an example from our recent experiment using the GSI hybrid for the GFS. So this experiment suggests that the hybrid can be better than the NCAP due to the use of the tangent linear normal mode strong balance constraint, which is available from the variational system. So in the next few slides, I'm going to share some of the pre-operational test results of the GSI hybrid for the GFS. We first conduct the single resolution experiments where the ensemble forecast and the single forecast will run at the same resolution. So what's shown here is the forecast error for temperature and wind, and the solid line is GSI 3D VAR, the other lines of the hybrid with different configurations. You can see clearly the improvement of the hybrid as compared to the pure 3D VAR. And the current operational hybrid system is run at dual resolution. The ensemble is actually run at half resolution of the control forecast. So what's shown here is NCAP operational parallel test for the GFS, and for like 5 months period. And the red one is hybrid, the black one is the 3D VAR. This is normally correlation, the higher the better. So you can see most of the time the GSI is better than the 3D VAR. The hybrid analysis also made a significant impact on the GFS ensemble forecast. So what's shown here is the hurricane track forecast during the 2011 hurricane season. And the only difference between the red bar and the green bar is red bar is using the GSI 3D VAR as the analysis, and the green bar is using the hybrid analysis. So you can see a significant reduction of the track forecast error by switching from the 3D VAR to the hybrid. As I mentioned earlier, we also extended 3D hybrid into a 4D. The current operation of GSI hybrid is 3 dimension. There's no time dimension within the data simulation window. So the temporal evolution of the error covariance within the simulation window is ignored. But we know all observations like satellite or radar data, they are actually spreading through the data simulation window. So we made this 4D extension. But this 4D ensemble VAR is different from the traditional 4D VAR, which requires tangent linear adjoint forecast model. This one doesn't need that part, so that makes it relatively attractive. Computational cost-wise, the 4D ensemble VAR is also much cheaper as compared to the traditional 4D VAR being developed for the GSI right now. So we test this newly developed the 4D ensemble VAR using the reduced resolution experiments. So this is the result for 2010, 1 summer months. On the left is the RMSE of hurricane track forecast. On the other hand, this is the geopotential height forecast for up to 4 days. The black one is the GSI, green one is 3D hybrid, and blue one is 4D hybrid. you can see there's a further improvement, okay, from the 4D extension as compared to the 3D hybrid for both the track and the anomaly correlation of the height forecast. Okay. So given the encouraging result of the GFS, there are efforts going on to integrate the GSI hybrid for regional forecasts, for example, HWRF, rapid refresh, etc. And I will only going to show you an example of GSI hybrid for HWRF in the next few slides. This is IRIN 2011, and we run HWRF integrate with the GSI hybrid, and it will simulate the radial velocity data from airborne Doppler radar. Okay, in this case, the red curve here is the life period of IRIN considered in this study, and the green curves are the 5 legs from one NOAA P3 flight mission. Okay, what's shown here is just a snapshot about the horizontal coverage of the airborne Doppler radar for one leg. Okay, you can see this horizontal coverage. Next, please. So what's shown here is the window analysis at the end of simulation window for the GSI 3D and the GSI hybrid. And we verify those with HRD Hurricane Research Division from NOAA radar window analysis. And if you look at the spatial distribution of the wind, the hybrid is actually much closer to the HRD wind analysis as compared to the GSI 3D. For example, it has multiple maximum centers. There is also maximum at upper levels, which is not consistent with what our understanding about the hurricane. Next, please. And this is a slice at 1 kilometer height. Again, this is our HRD radar wind analysis, and this is the GSI hybrid at 1 kilometer and GSI 3D at 1 kilometer. So the spatial distribution of the maximum wind, you can see the maximum at the northeast quadrant of the TC, which is consistent with the HRD analysis, but for the GSI 3D it's actually located at the northwest quadrant. Also, we noticed the center of the minimum wind, which is here, is not co-located with the center of the minimum pressure, which is not consistent with the typical TC structure. Next, please. So we also verify the two analyses using independent flight level wind speed observations. So the black curve here is observation, okay? And the red curve here is the posterior after the simulation of the airborne Doppler radar data. And the green curve is the prior before the simulation of the airborne radar data. So you can see on the left-hand side, GSI 3D bar, on the right-hand side is the hybrid. So you can see for both the prior and posterior, they fit the flight level wind observation much better for the hybrid as compared to the GSI. Okay. So to summarize, the GSI hybrid data simulation system was developed, and we show the significant improvement for the GFS, the global system. And this system became operational for the GFS 6 months ago. And we also made a 4D extension for the GSI hybrid and tested that for the GFS and showed further improvement. And the test of GSI hybrid with regional system also showed very encouraging results. And we plan to work with our collaborators to operationally implement the hybrid for regional forecasts. There are still a lot of things to do about hybrid data simulation, like how to further treat model error and sampling error, how to assimilate more advanced new observations, and how to optimize ensemble prediction through, for the ensemble within the hybrid data simulation system. Next slide. Next slide. Okay. So this is just some sample references. I actually missed an acknowledged slide, but I'd like to take this opportunity to acknowledge my collaborators from NOAA Ensembl, especially Derek Cluster and Dave Parrish, and from NOAA Earth System Research Lab, Jeff Whitaker, and my postdoc and student from OU, Yongzuo Li, Ting Lei, and Gavin Kuti. Thank you. That's all.
Thank you, Shubhang. We have time for a couple of questions.
Sorry. Can you repeat the question, please?
How does this hybrid technique differ from maximum likelihood ensemble?
Can you repeat the
How
question?
is this different from maximum likelihood ensemble filter?
Oh, okay. I think the spirit is similar because we are also we try to incorporate ensembles into the variational framework, but the way to realize the incorporation ensemble into the variational framework may not be the same. This is also using the ensemble common filter as a way to generate the ensembles.
Maybe I could add for MLEF. It's MLEF works fully in ensemble space, in a reduced rank space. However, your approach has the full rank space and reduced rank space.
Right. We have the flexibility to include the static covariance, and we can also apply the localization on ensembles to increase the rank within the variational framework.
Next question.
Okay. Can we go to the slides? The idea here is to, this is for the 3D hybrid. The idea here, we actually extend this observation term with the, for example, with the time dimension within the simulation window. And for the increment term, we also considered 4D ensemble perturbations. So this is in terms of the format of the equations. But in the sense, what it does is to rely on the temporal correlation of the ensemble perturbations within the simulation window to propagate the information from one time to the next, rather than using the tangent linear adjoint of the model to evolve the error covariance. I'm not sure whether it answers your question.
But that C is singular, right?
So the C here is the localization matrix. So the alpha is the extended control variable, and this B is the static covariance term. Okay, this is from the traditional, background term from a typical 3D var or 4D var here. And this is an extra term associated with the extended control variable. So this C here effectively is doing the covariance localization on ensemble perturbations. And this is a typical observation term. YO prime is still the innovation, but X prime is different from the traditional 3D var. It has actually two components. One is still the increment associated with the static covariance. The other one is increment associated with ensemble perturbations. This SKE is ensemble perturbations. So you can see this increment is coming from the flow-dependent ensemble perturbations. This is also modulated by alpha, which is constrained by the C. So effectively, this alpha is what it does to apply the covariance localization on ensemble covariance within this variational framework. So the 4D extension, okay, if we don't consider time localization, this is just a still spatial localization. The only change we made here is to first extend this into 4D, including the time dimension within the simulation window. We also need to consider this XKE at different times within the simulation window. So effectively, we rely on the ensemble perturbations covariance within the, through time to evolve the error covariance within the simulation window.
Thank you, Shuguang. While we are checking whether we got more presentations uploaded. Did we get one more? Yeah. Actually, the next should be by Dr. Hauser. Yeah. Do we have? Okay. So Dr. Hauser from Mason University will be giving a presentation on land surface data assimilation.
Thank you. Okay, I'm from George Mason University. I'm going to be talking more generally about land data assimilation with a few examples from snow. Go ahead. So our goal for land data assimilation is to optimally integrate land observations and predictions to produce better continuous time-space fields of various land surface quantities. Contributions are, these things will help us with understanding processes better, flood, agriculture, and drought prediction, as well as weather and climate prediction, help us to refine models, and help us to define what future observation needs are. So the pieces I'm going to talk about are observation, simulation, and assimilation, specifically for snow in this case. So we use the history of land data assimilation. We've used all these different methods. You heard about ensemble approaches and variational approaches in the last talk, but we've used a variety of them. And in the last 5 years or so, the community has really focused on the ensemble common filter. So a few things about the land that's unique compared to the atmosphere ocean assimilation is that the dominant land processes are horizontal. So the only ones, are vertical. The only ones that are horizontal are groundwater movement and temperature and water diffusion, but most of the processes are vertical processes. So we have good coupling vertically, but very weak coupling horizontally. That has implications for the kinds of models we use. At greater than about 100-meter resolution, we tend to use 1D physics models. So there's some ramifications of having that kind of assumption. The assimilation is relatively cheap, but the models don't really spread information out horizontally, and horizontal correlation in the observation model isn't accounted for. Another interesting piece of doing land assimilation is that most observations are at the surface. So we have surface skin temperature, soil moisture, snow cover, but we want to retrieve the full profile. So we get observations at the surface, and we want to retrieve the entire profile, and that can get quite tricky. So in terms of observations, these are the kinds of things we observe in the land system. We observe, of course, the forcing, and that is primarily used for offline land data assimilation systems. So if we're uncoupled, we can use forcing observations to independently drive this without having it be in an Earth system model. The second are parameters, soil properties, vegetation properties, and such, and we can use those to calibrate or reduce the bias in the model. The third are fluxes, what comes out of the model, like runoff and evapotranspiration. We use those to validate the system. And of course, for the assimilation, it has to do with the states, the soil moisture, temperature, snow, carbon, things that are stored in the model. That's what we want to assimilate. We've done a lot of different kinds of data assimilation. A few are listed here: soil moisture assimilation, snow cover, skin temperature, snow water equivalent. There's also been work on theory development, on applying advanced data assimilation theory to the land problem. And there's been some additional work doing runoff assimilation, groundwater assimilation, things like that. So let me talk a bit about snow as an example. So there's some unique aspects of snow. First of all, snow is extremely important to the climate system and to the water system. So a lot of the snowpack in the West is important for water supply in California, for example. In terms of snow and its unique data assimilation characteristics, what we tend to see is that the states disappear. So during the summertime, of course, we don't even predict snow in the models, and so we have to kind of reinitialize our error fields and whatnot when we get new snow fields in the winter. There's also, the snow models tend to be kind of unique. They arbitrarily redistribute the layers as the snowpack grows, which introduces some unique problems. There's also a problem with our observations, as we have observations of snow water equivalent that give us information about how much water is in the snow, and we also have observations about snow cover that tells us whether snow is there or not. Neither of them actually tell us about the layers or the depth of the snow, so we have to get creative on how we use these observations. We were motivated to look at this about a dozen years ago when we looked at operational forecasts. This is an example of a day-long cycle where we saw a snow field. If you look at one of these circles, the snow field over the course of the day melts off, And then the model was using an updating scheme and just putting it right back. So we got this kind of sawtooth pattern where every day the snow would melt, and then the update would put the snow back. And that caused huge problems in water balance and energy balance. So we did a simulation to figure out how bad this was. And this is air and water balance with just a bias in 10% on the shortwave radiation, and the air and the water balance on a 1 degree bias for the snow field. And I'm not sure why it's off the screen, but the bias was on the order of 50 millimeters per month in some of these areas at the edge of the snow field. So it was quite a large problem. We wanted to figure out how we could fix that. So we did some experiments with simulating MODIS snow cover. This is an example of a MODIS snow cover product. And this is what our model said that the snow water equivalent should be. Recognize these are two different variables. Snow water equivalence, how much snow is how much water is in the snowpack. Snow cover is whether snow is there or not. So we used actually a kind of an enhanced updating, a rule-based updating that took into account what was how the snow had melted or changed over time, and we assimilated the snow cover using this rule-based technique, and we got this resulting assimilated snow field. And this is the difference between the control and the assimilation. It's hard to see here, but this is the comparison with observations. So the dots are observations, the black line is our assimilation field, and this gray line is the model without assimilation. So we were able to correct the model very effectively with this very simple method. We moved on from there to look at assimilation of snow water equivalent with a Kalman filter. This is an example of snow water equivalent derived from the Simmer satellite in February 1979, and this is the modeled SWE. So there's quite a large difference in these. In some areas, it's a tremendous difference. But part of that difference is because there's a lot of errors in microwave-derived snow water equivalent. So we had to figure out how to isolate those errors. One of the biggest errors is when the temperature gets close to freezing, the liquid content in the snowpack increases the error dramatically. Additionally, if you get close to water bodies, even within a few hundred kilometers of a water body, liquid open water like the ocean, then you get air contamination in the microwave signal. So we spent a lot of time filtering out all these errors, doing the quality control, and we came up with these kind of results. So these are complicated plots. These are just different points on the map. But just to lead you through this, the observations, the original observations are the plus signs here. We have in situ data that's the kind of the ground truth in the black circles. The model without assimilation is this dotted line. The model with data assimilation, assimilating all the data, is the dashed line. When we do the quality control, we get this black line. And we get the same story from both of them, is that the quality control makes a huge difference on the performance of the system. So the last example I want to give you is to do with our attempt to assimilate both the microwave derived SWE data and the snow cover data. The issue here, as you can see, is they're very different resolutions. This is over a location in Colorado. So the SWE tells you how much water is there. The snow cover, just the snow cover fraction, how much the area is covered by snow. So how do you assimilate these two very different resolution and different kind of information into the land model? So here's a kind of a picture of it. We want to assimilate the SWE and distribute it down to a higher resolution where we have observations about the snow cover. What we did was we looked at a series of different kinds of filters. So mainly these accounted for different spatial characteristics. So from the very simplest, we just assimilate in the kind of 1D ensemble common filter at the point, the highest resolution, the nearest observation we have. Then we can increase the spatial scale of what we look at, make it more complicated, and look at an area around this. Increasing that, we can look at increasingly more complicated spatial scales or 3D Kalman filters as we increase the how the observations from the vicinity influence each point. So here's the results. We get more complicated to the more complicated 3D filters as you get down here to the bottom. Here's a kind of this is a identical twin experiment where we have a nature run in an open loop. So what we want is for our filter result to look like the nature run. And in this case, the more complicated three-dimensional Kalman filters were the most likely to give us a realistic looking field. So we were hoping that it would be simpler than that, but that was the result. We've, over working with NASA Goddard and some of my colleagues there over the last 10 years, there's been the development of these land data assimilation systems. So putting a lot of the different kinds of data and models, data assimilation techniques together, they've produced these global fields of snow water equivalent, of surface temperature, soil moisture, that kind of thing. And one of the goals with that is to try and initialize climate and weather prediction models. So these are example from the 1988 Midwestern U.S. drought, where we initialized the seasonal forecast with these GLDAS data assimilation land fields. And these are observations of precipitation. So we wanted to see what the impact of precipitation would be. So observed precipitation. This is the seasonal forecast model with no initialization of soil moisture. This is predicted with initialization fields from our offline land data assimilation system. And this is scaled to climatology. So this is scaling the offline model to the coupled models climatology. And what you find is that we do a much better job predicting the drought when we have given the model better information about soil moisture. So that's very encouraging. So in summary, there's been a lot of progress. I talked about in land data assimilation, I talked about snow assimilation, but also in skin temperature, soil moisture, runoff, groundwater assimilation. There's continued work on looking at things like evaporation and carbon assimilation. We've learned a lot of things about the consequences of doing data assimilation in a land model. For example, making sure you know about biases. In the case of the weather prediction model I showed you, where the snow disappeared and then was put back each day, that had to do with a temperature bias in the model. So no matter how sophisticated your observation is, if you have another process that's influencing the bias of the model, that has to be accounted for. Future directions, there's new observations that will be coming online in the next few years, like the soil moisture active passive mission, and looking at doing, we've actually done some of this mass energy conserving data assimilation techniques, and coupled assimilation, of course. Thank you.
Thank you. We have time for 2 questions. Maybe I have a question. So when you mentioned coupled data assimilation, is it coupling with the atmospheric model, and which model do you have in mind?
Well, the primary one we'd like to do that with, of course, would be the NCEP and WRF model. And there's been some studies doing some of that coupled modeling, but to make it truly operational takes a bit of a lot of testing and making sure you don't make anything else worse in the model. So that's where ultimately we'd like to go with this.
You mentioned the land model physics can be biased. Do you have any idea how do you correct that bias?
Yeah, so land model physics, just like any model physics, can be biased. So one of the ways that we correct biases are by doing calibration. So but there's also ways to do nested filtering where you can do calibration at the same time as data assimilation, and we've looked at that a bit too, so I think that's a promising, where you can actually fix the bias as the model runs. Thanks.
Thank you.
Thank you, Dr. Hauser. So we will be moving on. I'm so sorry, we are so sorry that we do have some technical difficulties, that some presentations didn't get uploaded on time, and that happens. Oh, news are good, they are coming in. Thank you for your help. So then we will be moving to the next presentation to be given by Dr. Baker from University of Reading. And just
This one cannot. The right one, Baker.
yeah, yeah, it should be that one. You can.
It said cannot be read.
We need some help still. But good news is that the presentation is in the computer. So while we are preparing for the presentation, I just would like to ask every speaker, after you finish the presentation and once you get a question, please repeat the question that everybody can hear. And the other thing, we have to apologize because of these lights. Sometimes they are really bright, so maybe you have to look down a bit. Sorry.
Is it PPS? Is there a dot PPS? It shows dot PPS. Yes. G2. Did they? Oh, no. Oh, sorry.
Sorry, there is one more change of plans. Because there was issue with this presentation, we will switch with the two presentations. We will use the next one that was kindly offered by Judith to go with, because it's ready. That's on the Mac. So the next will be presented by Judith Berner from NCAR.
Hello, good morning. Thank you very much. Is this the... So my name is Judith Berner. I have been working on model error representations for many years. However, I'm new to data assimilation. However, I have some very skillful co-authors, Su Young Ha from NCAR, who did all the experiments, and Chris Snyder, who is an expert on ensemble Kalman filter. Why do we need model uncertainty representations in mesoscale ensemble systems? There are large uncertainties in the mesoscale ensemble systems, and for example, on the mesoscale, land surface schemes, boundary layer parameterizations, and just altogether unresolved processes below the truncation level of the model, of the resolution. This can lead to unreliable and overconfident ensemble forecasts, and in particular, insufficient ensemble spread can lead to poor analysis and forecasts. This is a problem in forecasts, but it is even more a problem in ensemble data assimilation, where there is the danger of the ensemble system to collapse. So just to show you some motivations, those are forecasts from the WRF ensemble system, mesoscale ensemble system, and this does not involve any data assimilation. It is just forecasts started from GFS initial conditions. And I'm showing you 3 ensemble systems throughout the whole study. The control forecast is shown in blue. It's just a 10-member ensemble system. SCAPs is a stochastic parameterization, the stochastic kinetic energy backscatter scheme. And I will talk about about the scheme in more detail later. And then we have a multi-physics schemes, which is shown here in red. And those are just forecasts. This is forecast lead time. This is spread error for the zonal wind U at 10 meters and temperature in 2 meters. And we can see that if we have a model error representation, so this is the green and the red line, then we have more spread over the control ensemble system and less error. And this is reflected in the Breyer scores and the forecast still scores, again as function of forecast lead time, where if you have a more model error scheme, you actually have a more skillful model in both temperature and wind. So when we saw this, we thought, it would be really nice to look how these schemes perform in the ensemble data assimilation context. And then ultimately we hope to do it in both, do an end-to-end system where we look at the performance of model error schemes in the assimilation time step and the extended forecasts. So a bit more details about the 2 model error schemes I'm introducing here. One is the stochastic kinetic energy backscatter scheme, or SCAPS. It is based on the rationale that a fraction of the subgrid scale energy is scattered upscale and acts as a random stream function and temperature forcing for the resolved scale flow. In this context here, we can just consider it a additive noise that has spatial and temporal correlations. This scheme has been used in forecasts for mesoscale ensemble systems. It's operational at a number of centers, including ECMWF, where it is part of the operational system. Has the original reference is Schütz 2005, and there are some differences to that scheme, which is that here in the results I'm showing here, it is assuming constant dissipation rate and also introduces potential temperature perturbations. The second model error scheme is just a multi-physics scheme. So we're having a 10-member, 10 different physics combinations. They have different combinations of surface model, microphysics, boundary layer, cumulus, and radiation schemes. So each of the ensemble member uses one of these 10 suites. Each suite is employed 5 times in the 50-member ensemble used in the ensemble data assimilation. And this number 5 here, this is what we call the control physics. So this is the physics suite that is used for the control simulation, and it's also used for the simulation with SCAPs on top. So the SCAPs simulations have only one physics scheme. So here's the setup of our ensemble Kalman filter of our data simulation. We use the ensemble Kalman filter, which estimates flow-dependent background covariances from an ensemble forecast. And my collaborators are experts on that topic. For the analysis step, the ENKF uses the Data Assimilation Research Testbed, or DART system. And for the forecast time step, we use the short-range ensemble forecast using non-hydrostatic advanced research WRF model version v3.3. This is the experiment setup. We have 2 domains nested. Here's the inner domain with a resolution of 15 kilometers, and the outer domain over the contiguous United States with a resolution of 45 kilometers. We have a 50-member ensemble. The initial conditions and lower boundary conditions are used from GFS data. The filter has a half-width localization radius of 300 kilometers in the height and 4 kilometers in the horizontally, and 4 kilometers vertically. And the cycling period is continuous 3-hour cycling over a period of 1 month in June 2008. The assimilated observations are shown here. It's RAOP, MEDAR, Marine, and ACARS data. And so when we do the verification of our analysis and our prior, we will actually verify against an independent, non-assimilated data source. In this case, we use the Mesonet network. Here's the verification. I'm moving now over to the results. Here's the verification of surface analysis against independent observations. Here it's shown for the meridian wind in 10 meters and temperature in 2 meters. And shown here are the RMS error. So the lower, the better. The control simulation is shown here in blue. And we see that if we have a model error representation, the RMS error in meridian wind and in temperature decreases, more so in temperature than in vertical wind. Up here is the statistics, just the RMS error averaged over the whole cycling period. And we see that for meridian wind, the best result is obtained for the SCAP scheme, while for 2-meter temperature, the multiphysics scheme is outperforming the SCAP scheme slightly. However, it is clear from these results, these are analyses, that the analysis get better if you introduce a model error representation. These are now priors. The priors in the study are 3-hour forecasts. And again, the verification is against independent Mesonet data. Here we're showing spread and error. And again, same color, same scales. So what we would like is more spread because we have an under-dispersive ensemble system. We would like to have more spread, so the higher here and less error. That would be the ideal. This is now just shown for meridian wind in 10 meters. And we can see that indeed here there is more spread if you have a model error representation. And in this, if you look at the RMS error, we actually are in the situation that with the SCAP scheme we have more spread and smaller RMSE, which is what we want. That's ideal. The physics scheme for this particular variable has more spread and larger RMSE than the control. In this situation, you don't really know what to do. You can do a Breyer skill score to see if you have a more skillful forecast or not. And those results are qualitatively similar for the zonal wind in 10 meters and for temperature. What we've done next is to look at the effect in the extended forecast. These are forecasts up to 72 hours. The forecast model is just the model with the control physics. So those 3 simulations only differ in their initial condition. And they have been initialized with a mean analysis from the 50-member analysis created by the ensemble data simulation. We just take the mean and then do one extended forecast. So the differences, again, are only in the analysis, and we can see that these sort of initial differences really are visible at least to 36 hours, but you can probably see a difference up to 72 hours. This is for temperature in 500 hectopascal. And so this is the RMS error, and we see that the smallest error here is, again, with the SCAP scheme up to 36 hours. Those are just vertical profiles of RMS error and, in this particular case, bias of the 3 experiments, just to show you that this is not just near the surface. It's really a result we see throughout the free atmosphere. And we see, again, that in this for temperature here, except near the surface SCAPs. This is verified against soundings. We see that the SCAP scheme does do better. Slightly better than the physics scheme, and they both do better than the control physics. Yeah, so I should say that the SCAP scheme tends to outperform the physics scheme in forecasts in the free atmosphere, but near the surface we get mixed results. Finally, a word about inflation. All experiments shown so far employ adaptive inflation to prevent the collapse of the ensemble system. This inflation has been described, it's part of the DART system in Anderson 2009. It increases the spread to remedy the total effect of all causes of underdispersion. And this includes, but is not limited to, model error. It is also to account for sampling error in the sense that there are regions where the observations might over-constrain the analysis, like near airports and in big sort of close to cities where there's lots of data available. The assimilation with SCAPs and adaptive inflation is slightly better than SCAPs alone. This is shown here. So here we see that the SCAPs without inflation is shown in blue and with inflation in red. And this is RMS error, so the red line is slightly under the blue line. It makes the assimilation a bit better to have SCAPs and inflation. And we can see this reflected in the spread. If we have SCAPs and inflation, we have more spread than if we have only SCAPs. However, if we use SCAPs only and compare this to a ensemble data assimilation that uses inflation only, then the SCAP scheme has a much better effect than the inflation alone. So one could argue that the SCAPs can replace the adaptive inflation factor currently in DART. I'm coming to my conclusions. Including a model error representation in the ensemble data simulation resulted in a better analysis in short-range forecast. We've conducted significance tests not on all metrics, but we've done it on priors, and we see that these differences are significant at the 95 confidence level. However, we only looked at 1 month of data in summer 2008, which is limiting. Future work. We noticed that the order is reversed when we use the ensemble data simulation. It seems that the physics scheme is a bit better than SCAPs in forecasts only, but if we do the cycling, then it seems that SCAPs is better than the physics scheme. We're trying to understand that better. We think that this improvement is the result of using a model error scheme in the analysis step rather than the forecast step. The stochastic perturbations introduced by SCAPs seem more beneficial than the large instantaneous changes resulting from the inflation, adaptive inflation scheme. And our future work is aimed at a better understanding why including a model hybridization is so beneficial at the data simulation step and what the role of the bias is. Thank you very much.
Thank you. We have time for two questions, please. Okay. Person on the back. The person on the back was before you, and then you are the next. Yeah.
The multiphysics ensemble is kind of a strange way to represent your model uncertainty. Is there any indication that maybe having some sort of quantification of uncertain model parameters might produce a more better forecast ensemble?
To summarize the question.
Oh, thank you. Yeah. So the question was maybe a multi-parameter model error scheme would be better than a multi-parameterization model error scheme. Is that correct? I've looked at this not in the data simulation context, but I've looked at it extensively in forecasts. And so far, we are not able to introduce enough spread with a multi-parameter scheme so that the error growth on the sort of short-range forecasts is very small. So it's not very efficient if you choose parameters that the experts are happy with.
Next question.
My question is actually similar. I was wondering if you had tried different stochastic parameterizations for the physics rather than the stochastic, well, in addition to the stochastic backscatter. I mean, there are different ways of introducing
Again, so the question is sort of a generalization. There may be other stochastic schemes that are better than the one I presented. I've looked at this a lot in the context of forecasts with this particular model, not in the context of ensemble data assimilation. In general, I see the more spread a model error representation introduces, the better its skill is. This might just indicate that we have a highly underdispersive model here, ensemble system. And in general, if we combine different model error schemes, be it multiphysics and a stochastic scheme, two different stochastic schemes, or three different ones with a multiparameter scheme, then we get better results in the forecasts. And we would need to redo the cycling results with that if we have the resources. I can point to papers, the second paper and references in where we have done a subset of those comparisons.
Okay, thank you. We need to move forward. I have good news. All presentations are in place, and we checked them. They seem to work. I cannot absolutely guarantee that the movies will work, but I do hope that they will. Now we will finally have Laura Baker from University of Reading to give us her presentation.
So I'm a postdoc at the University of Reading in the Department of Meteorology, and the work I'm presenting today is part of the NERC-funded project Diomet, which aims to look at the diabatic influences of mesoscale structures in extratropical cyclones. So my particular piece of work is looking at errors in high-resolution forecasts. So in weather forecasts, errors originate from various different sources. These are the initial conditions, the boundary conditions, and model errors which occur due to the parameterization of subgrid scale processes. So as we go to higher resolution and try to represent smaller scales, model errors become more important. So we want to add some representation of these errors. So the approach that we've used is a perturbed physics approach in a convective scale, so 1.5 kilometer ensemble system. And the questions I'm aiming to answer in this presentation are, how does this representation of model error affect the spread and the skill of the ensemble? So the system that we're using it's the UK Met Office model, and we've used two of their operational ensemble systems. So the first is MOGRIPS G, which is the global ensemble system, which runs at, it has about 60 kilometer resolution at mid-latitudes. The second is the MOGRIPS R, which is covers this North Atlantic and European region here. That has 18 kilometer resolution. And so both of these have 24 ensemble members, so the control, and 23 perturbed members. And so our system is a research EPS, and it covers this very small region here, which covers the southern UK. So this takes the control member from this comes from a 3D VAR analysis, and the initial condition and perturbed lateral boundary conditions come from MOGRIPS R. So we have an hourly cycling ETKF. And then in the case that I'm showing today, for the period of interest, the 6 hours here, we've not included the hourly ETKF cycling, but it's still forced by the hourly LBCs from MOGRIPS R. So the method that we've used to simulate model error is called the random parameters scheme. So this is used operationally in MOGRIPS G and MOGRIPS R, but hasn't previously been used for a convective-scale ensemble. So what this scheme does is it takes a set of parameters from various different parameterization schemes, such as the boundary layer scheme and microphysics schemes, and it adds random perturbations to them, so treats them like stochastic variables. So each ensemble member has a different set of random perturbations for these parameters. This equation here shows the kind of basis of the model. So you can see that, of the scheme, sorry. You can see that PT, which is the kind of new value of the parameter, depends on both mu, which is the default value, and PT minus 1, which is the previous value. This epsilon term is the random element, so it's taken from a uniform distribution within this range. So in our sort of modified version of the scheme, we've identified some extra parameters that we can perturb, which are different from those in the kind of standard version of the scheme. So we've got 7 boundary layer parameters and 19 from the microphysics scheme. So we keep the parameter values fixed for 30 minutes between subsequent calls of the RP scheme. So the case study we've used is this case on the 20th of September last year. So I mentioned earlier the DIMET project, and this was one of the cases which, as part of one of the DIMET field campaigns, we flew through it and took some extra measurements. So we aim to try and use this extra observation data later on in our work. So this system had a front crossing the southern UK. It also had this interesting sort of triple banded structure that you could see in the radar, but wasn't captured in either the operational high resolution forecast and does not appear in our control simulation. So this is just a quick animation of the passage of the front. So on the left is the radar data, and on the right is our control forecast. So you can see these 3 bands come in the radar, but then they don't appear in the control forecast. So one question we were interested in was whether any of our ensemble members capture this triple banded structure. And the answer to this is no. Although some of them do have rain kind of in the correct location corresponding to the second band, this middle one. I think this is more to do with the kind of general shift of the rain band rather than capturing a double banded structure. So the next slide shows the same ensemble but with the RP scheme applied. So you can see that, is it possible to go back? Or? Okay. So you can see that the effect is quite small and really it only affects the smaller scale details within the rain band rather than the larger scale features, which is what we'd expect because they're driven by the driving model. So in terms of the effect on the ensemble spread, these plots show the ensemble spread as it varies with time during the 6-hour forecast. So the black line shows the standard ensemble with no representation of model error. The blue line shows this ensemble but with the RP scheme applied, so with this representation of model error. And the pink line shows model error only, so no initial condition perturbations. So really 24 different sets of random parameters applied to the control forecast. So what you can see is that in the top 2 plots, you can see that adding model error has increased the spread compared with the control ensemble. And in temperature, this actually continues to increase throughout the forecast, whereas in the 10-meter wind speed, this kind of has a kind of fairly constant effect. From the pink lines, you can see that model error alone does have some effect, but this is much smaller than the effect of initial condition perturbations. The bottom plot shows what happens to the rainfall rate. So you can see that the effect of this RP scheme has actually introduced these kind of periodic peaks in the rain rate. And the timing of these corresponds to the timing, the 30-minute interval that the RP scheme is applied. So obviously this isn't ideal because it seems to be kind of kicking it a bit too hard. So we looked a bit further into this, and we tried running the ensemble just fixing the parameters throughout, so not updating them every 30 minutes. And that's the pink line shown here. So what you can see is this has actually reduced the spread compared with the original ensemble, which was unexpected. And we're still looking into exactly why this is happening, but we think it's due to the kind of interaction between different parameters that were perturbing. So another thing this led to was that we found, so the bottom plot shows the total precipitation at each time, the mean of each of the ensembles. So you can see that the blue and pink lines, which have the RP scheme applied, are actually reducing the total precipitation. So they're basically introducing a bias. So this is sort of still work in progress to try and work out exactly why this is happening and what parameters are causing this. In terms of the skill of the ensemble, these plots show the CRPS, Continuous Rank Probability Score. If you're not familiar with this, then basically a lower number is good. So in these two plots, at the beginning of the time, you have quite a good skill, and then this reduces with time, and then actually seems to increase later on in the forecast, which is probably due to the information coming in through the boundaries. So what you can see from these, which I think is related to the previous slide, is that adding this representation of model error is actually reducing the skill of the forecast in terms of rain rate and rain accumulation. For other variables, that it has very little effect, which is good in that we're not reducing the forecast skill. Interestingly, in this particular case, the skill of the surface temperature is actually increasing with time. So just to summarize what I've just said, so we're developing a method of representing model error in a convective-scale ensemble, and we're using the random parameter scheme, which is a perturbed physics scheme. So using this method to represent model error, it does successfully increase the spread of the ensemble for temperature and wind speed, but for rainfall rate, it introduces a kind of periodic unphysical peaks in the spread. This can be removed by keeping the parameters fixed throughout, but this actually has the effect of reducing the spread. In terms of the skill, the addition of model error has a small effect only on the skill of the forecast, but the skill in the rain rate and accumulation is actually reduced, which is probably due to this bias that I mentioned about reducing the total rain rate. So I think what I've said is clear that it's still a work in progress. So what we're doing now is looking at more cases, because obviously we need more than one case to look at, and looking more closely into why we're encountering these problems, to try and kind of work to improve this scheme as a method of representing model error. So things we aim to do in the future is to use the extra observation data that I mentioned from the Diamet field campaign to try and compare our ensemble statistics with information from the observations. We've also run a large, so 92-member or 92-member plus the control ensemble, and we're using this to look at how the error covariance statistics change with increasing the ensemble size, so to see whether they converge somewhere before 92 members. And we're also looking at balances at convective scale. So in particular, at these scales, the hydrostatic and geostrophic balances can no longer be assumed to hold. And these are assumptions that are kind of assumed in data assimilation systems. So we're trying to use the ensemble data that that we've got from these systems to see what alternative balances do hold and therefore could be imposed in convective-scale data assimilation systems. Thank you.
Thank you, Laura. We have time for 2 questions, please. Judith?
So presumably, when you fix the parameters, you end up have different biases for each ensemble members. If you look at the member-specific biases and see if some make it better and some make it worse, and some maybe the resulting bias is negative, or if all lead to a worse rainfall.
We haven't done that much work looking at individual members. I think, oh, it's not hearing well. So that
Your presentation back?
it is okay. It doesn't matter. So from the sort of stamp plots I showed, you could see that in some members the amount of rain was increased and some was decreased. So I think they're not all kind of introducing a bias in the same way, but the kind of the overall result is a negative bias.
One more question? Okay.
You perturb your parameter randomly and then you hold it for how many time steps?
So our time step is 50 seconds, so it's
Okay, a lot.
yeah, a long time.
The point I'm trying to make is that if you randomly pick something towards the end of your distribution, then you're stuck with it for like a lot of time steps. And
Yeah.
it occurs to me that if you keep your spread while reducing those spurious peaks by sampling the random parameters more frequently.
So as in applying it more.
Well, I mean, the thing
More
is
than-
that if you get something more towards the center of your distribution, or if you have a peak distribution and you're not sampling in the tails so much, I mean, you'll get some negative feedback or negative interference of the system of your random parameters, so you're not stuck with keeping a large one for several hours.
Yeah. So the kind of thinking, the reasoning behind keeping them held for a reasonable amount of time. So in the kind of original RP scheme that's used in the lower resolution models, they're actually held fixed for 3 hours. Although that's a sort of similar number of time steps. The reason we've kind of chosen to keep them held for a reasonably long time is because we wanted to try and think about the timescales of the processes that they're representing. So we didn't want to kind of keep changing it too frequently, because then the kind of new state wouldn't have enough time to take effect before it's then changed again. It's something we're still looking into about.
You can do that and still put in more. We can talk.
Okay.
Thanks. Next is our third invited presentation given by Dr. Sue Haupt from NCAR on data assimilation for applied meteorology.
Thank you, Jenny, and thank you for inviting me to be here. This presentation is going to have absolutely no details. Instead, it's going to be a little bit more philosophical in nature and then show examples of my point. So we've seen the same point presented in several different ways already this morning, but I choose to look at the equations of motion in terms of a dynamical system. And in this case, it's a nonlinear dissipative dynamical system. So as we all know, Lorenz in '63 started talking about sensitivity to initial conditions. It admits chaotic solutions. And because we have a chaotic attractor, we always are going to have an uncertainty due to the sensitivity to initial conditions. How do we deal with this? How do we know we can stay on the correct trajectory? Basically, by doing assimilation. Now, let's back up a moment and think about, and we've heard a lot about ensembles today, but oftentimes what we want to predict is a realization rather than the ensemble. And as an example of a realization on a very fine scale, I have some photos that were taken within less than an hour of each other of some smoke plume experiments that we did back in State College, Pennsylvania. And you can see that although the transport is in the same direction, each of the smoke plumes looks different. It depends on the exact state of the turbulence that was mixing these smoke plumes at the time. So how do we model this? Basically, all of our models that use Reynolds averaging base it on ensembles. And as pictorially, we can see that. If we would take 10 of these smoke plumes, all measured on the same day, very close period of time, superimpose them, and we get something where you can now see the envelope. And that ensemble average is something you can model more. Now, in terms of numerical weather prediction, we've seen this quite a lot today. What we do is we run ensembles. But each ensemble member represents a particular realization that might occur. Now, I live in the applied meteorology world. For applications, what users really want is they want to know which realization is going to occur this time. Some examples are flow over terrain, atmospheric transport and dispersion. If we're on a larger scale, a decision maker may have to decide, if it's a hazardous release, what areas to evacuate. You can't base that solely on a large range ensemble. You need to be able to recover the particular realization and give a prediction of the realization. Now, one of the areas I work now is wind power, and for wind power prediction, we often need to know when ramp in power is going to occur. This particular case is of a cold front passing through Colorado. This particular utility saw a ramp up of 800 megawatts, followed by a ramp down in just a 4-hour period. The decision maker at the utility has to plan how to schedule power so that they can use the wind, but when it drops down, they make sure they have reliable power to fill in. They need to know when that's going to occur and to predict the magnitude and timing of ramps like this. So, how do we deal with that? Start with our equations of motion. Okay, we know that we're going to need to use some sort of dynamic assimilation. If you have a realization that's occurring, in this case, a large eddy simulation realization, how can we assimilate those data? Okay, now, just for illustration purposes, I'm going to talk in terms of Newtonian relaxation, just because it's something that can easily be stuck on the end of the momentum equations, where what we want to do is minimize the difference between the forecast and the observations. That means that you have to have some sort of observations sampling the flow. If you can sample the flow, you can do that minimization. Now, of course, you can do that in various ways. The Newtonian relaxation is basically nudging. When it's done dynamically, it's real-time four-dimensional data assimilation. 4D VAR does the same thing, basically by optimizing ways to minimize that error. And then I'll talk a little bit about more of an empirical method, genetic algorithm variational method. Let's look at a couple of examples on how you can recover this information. beginning with blending mesoscale model into computational fluid dynamics. And the purpose of this was to get the specifics of flow over topography in a way that the NWP models aren't able to. So the first step is just harvesting a flow out of WRF, Weather Research and Forecasting model, setting up a grid for the computational fluid dynamics model that is really more at scales on the order of 30 to 40 meters, so we can get the flow over these two ridges that occur. But in addition, we want to assimilate the WRF data at the grid lines so that we can get the profile of the data. And we do that again, in this case, just for simplicity, using Newtonian relaxation, applying Cressman spreading. When we ran the CFD model, we found that the changes in the flow were persistent in time and space, and that we were able to assimilate these NWP data into the very fine scale model. Next example, back to these smoke plumes. I love these smoke plume experiments because that's reality, where we actually saw what happens. You can see the eddies in the flow, altering the flow. This is just trying to set up what the problem is. I was on the camera behind that, and you can see the plume meandering. This often occurs where you have turbulence at various scales. Sometimes you have this outer flow where you're meandering a plume. You might be able to resolve that if you model well, but you have an inner flow that is also dispersing a plume. So we started by setting this up as a very simple problem where we're resolving the meander that was set up originally, but we are not resolving the dispersion that occurs according to Gaussian dispersion. We're going to use a genetic algorithm variational method. All it does is it uses a genetic algorithm to optimize the difference between the observations and the data. We're going to sample from this plume, and we find that at the outer scale, we can recover the plume the plume centroid motion. That you can see right at the beginning, the genetic algorithm was not able to get the first few because we didn't have enough data sampling. But once we did, you can't even distinguish the difference in the movement of the center of the plume from what happened. Okay, if you look at a recovery in the picture, we get a plume that looks very much like what we started about. What about that inner variability, the dispersion? Can we recover that piece? This is the horizontal dispersion coefficient, and we found that the genetic algorithm did recover the temporal changes in that. The vertical dispersion coefficient, much harder because we're only sampling in 2 dimensions. Again, at the beginning, it was very difficult, but we did manage that even to recover that inner dispersion information as well. Now, that was an identical twin experiment where we started with a really simple. Let's go back to the large eddy simulation where we have a meandering plume dispersion, but it's more realistic turbulence. And if we're going to apply the genetic algorithm variational technique again, so if we take the simulation, harvest a dosage at 1800 seconds, can we recover that by trying to match the wind direction, the dispersion in both the horizontal and the vertical? And indeed, we did. The paper shows that you can also see that the trajectory of the centroid, again, matched quite well, and we also showed the RMSE was decreasing. Okay, that was a simple dispersion problem. Let's go back to that energy ramping problem. How do we recover information about ramps in wind? Okay, here on the top, we have a time series of a run of WRF. This is a 3-kilometer run of WRF with, at a wind farm. You can see several ramps occur here. Let's focus on this one, this one. You can see here, without having any data assimilation from the wind farm itself. Now, of course, WRF was run in data assimilation mode, but we didn't include any from the wind farm. You can see that the actual deviates quite widely from what was observed. However, when you did assimilate data from the wind farm, you see you get some of these ramps beautifully. Now, this one used the four-dimensional real-time data assimilation, and in fact, we got the root mean square error improved by 17%. You can also look in terms of some other variables. Now, that's not the only method. What if you need very short-term assimilate? You want to do a very short-term prediction. If you want to do it on the hours, say 15 minutes to 2 hours, you can apply the variational Doppler radar analysis system. And this is work done by my colleague Jenny Sun, sitting right here. And I want you to watch this movie of here you have a convergence line, and it's approaching the wind farm. And watch what happens behind this convergence line. You see the wind vector increase in magnitude as well as change direction. Okay, so for the grid operators sitting in their control room, having this kind of situational awareness, running a model. This assimilates Doppler radar data using 4D VAR into a cloud scale model. This provides the operator with the information they need to be able to control energy and provide us a reliable energy while still making use of that low-cost wind energy, because they can see this happening in the system. Okay, so let's summarize. Okay, I'm trying to make the point here that yes, we have inherent uncertainty in atmospheric flow. The users of our information really want information about the particular realization. Now, we know that as meteorologists, we often choose to quantify the uncertainty because it is very difficult to get after. But if we want to get at the information about that very particular realization so the decision makers can use it, then we're going to have to do something. And dynamic assimilation, where we're constantly updating the information, is an approach that is effective, and it helps deal directly with the sensitivity to initial conditions. Where are we going in the future? Okay, one of the difficult problems is predicting clouds. Okay, NWP models do that, but in a lot of sense, we try to just predict cloud fraction. Well, at NCAR, we are anticipating an award of solar power forecasting. We have to be able to forecast clouds. How are we going to do that? With assimilation. On the longer scales, we're going to be assimilating satellite data into a special form of WRF that is configured specifically for solar power prediction, that includes enhanced cloud physics parameterizations, convective parameterizations, etc. On moderate scales, 15 minutes to 2 hours, we're going to be assimilating data from total sky imagers into VDRAS. These total sky imagers are vertically pointing cameras, fisheye lens. You can see the clouds. If you put 3 of those in the field, you can trace the clouds, you can estimate the depth, etc. So being able to assimilate these data into a cloud scale model, we think will make a big impact. And on the very short scale, 5 minutes to an hour, the best we can expect to do is probably advect those clouds. So again, by observing them either by satellite data or total sky imagers, we believe that we'll be able to advance cloud forecasting. So thank you.
We have time for a few questions.
Okay, the standard data that NOAA does, but we're going to be applying techniques, making it faster, using GSI, to assimilate those data.
Are you talking IR or are you talking microwave? Or are you talking both?
All. Anything else?
Okay, any other questions? I just have comment. I think the atmospheric flow, the predictability really depends on the scale, right?
Yes.
So it's very important to be able to distinguish, for this scale, what is predictable, what is not predictable, right? Instead of mix everything together to an ensemble. So.
Okay, thank you, Jenny, and that's a very good point. That's exactly why I was showing examples at all scales, from the very fine scale dispersion problems through these larger scale problems. And we, of course, have the outer flow that's resolved, the inner flow that's unresolved, but we can still recover characteristics on both with the observations. So thank you.
Okay. Our next presentation is given by Dr. Kurapov, also invited presentation. He will talk about, well, he will tell you what.
Good morning. I'm Alex Kurapov, Oregon State University. I like this session because it shows implementation of data assimilation methods in different branches of geophysical sciences. So I guess I present something about oceanography. Our group at Oregon State has been involved in the simulation of satellite in situ data and coastal shelf scales like shelf and the ocean adjacent to the shelf. And we even have the forecast model, which you can Google and check. Today, I'm talking about quite different scales, even smaller scales. We got recently involved in a simulation project supported by Office of Naval Research. It's about assimilating remotely sensed data in a nearshore environments. It's the environments where the flows are in part driven by the breaking waves on the beaches, all right? So my co-author is Tuba Oskanhala. So what the data people are trying to get in the nearshore environments, like beaches and river inlets, they use radar and optical methods to gauge information about wave speed. There's some information about waves, and also the information about currents in the nearshore environments. And we will try to assimilate this to actually infer the bathymetry. So bathymetry can change very rapidly after passing storms, and it's a very important parameter in many applications. I understand like people from different backgrounds are in the room, so if you're new to nearshore environments, at least you can look at this presentation as an example of simulation in a coupled model. So we have two models here, the wave model and the circulation model. The wave model is forced at offshore conditions. In this picture I show the example of bathymetry. So I'll be talking about the idealized study. It's actually, my results come from the twin experiment, so it's pretty simple still. So this is the coast, and you have nearshore bathymetry. You have like a sandbar here, with some troughs and shallow regions. So the waves coming at an angle from offshore, they refract around bathymetry. So this lower plot shows the wave propagation. Computer uses the wave model. And also waves break over the bar and near the shore, and this breaking process delivers energy to the flow, and the longshore currents start, and they are non-linear. They kind of may create swirls and meanders. So we're trying to get velocities from those flows to get information about bathymetry, right? So at a more the wave model at a more abstract level. So the key here is that we integrate those equations for the wave propagation and for the conservation of energy from offshore to the coast. Now, if you want to write the adjoint model to this model, you would write the adjoint would integrate from coast to offshore, providing sensitivity to bathymetry of bathymetry and offshore conditions. The right-hand side on this equation is the dissipation, which depends nonlinear on bathymetry. And using those parameters, you can compute the steady forcing of the circulation model, right? So the message here that despite this is a very nonlinear model, it's differentiable with respect to bathymetry, so you can write the adjoint to it. And we did do that using standard technique by Gearing and Kaminsky, but we did it by hand. So the circulation model uses that forcing from the wave model right here. So it's a standard shallow water model. It's nonlinear shallow water model, continuity, momentum equations. So it's forced by steady forcing, which can be spatially dependent. And also we have linear friction. And depending on the linear friction coefficient, the character of the flow can be different. Can I go back? Yes, yeah, this is, yeah, good. So, so if the coefficient of the bottom friction is small enough, then in response to the steady forcing, we have a non-steady, unsteady flow. It can be like equilibrated waves flow shown on this upper panel. So each panel shows like a snapshot from the model, velocities and vorticity as contours. Or if you decrease the friction coefficient even lower in response to the steady flow, you have the kind of aperiodic regime with a continuous wave number frequency spectrum. And we try to do twin experiments using both cases, right? So you can get this nonlinear flow, you try to sample velocities from that flow and infer bathymetry, which is a steady function. So this is the schematics of the coupled wave circulation model again. Bathymetry now is an input parameter. Bathymetry affects the wave propagation. And the wave model gives you estimates of the K and L would be components of the wave vector, or the wave, kind of wave speed, if you like. E is energy. You can also get a dissipation from this. Also, it computes the F, the forcing of the circulation model. Circulation model uses that steady forcing and initial condition, and you get the velocity. So our concern is how you assimilate velocities and get back to correct bathymetry. All right. So this is the schematics for the tangent linear and joint model. The tangent linear model, the information flow is very similar to the nonlinear model. So you have perturbation in bathymetry, and you get perturbation in velocity eventually. So you can see like there are two paths here. So perturbation of bathymetry affects wave field, wave model, the forcing and the circulation model, and also directly there's direct contribution to the shallow water equations from bathymetry. So in the adjoint model, so that's how you write the adjoint model. Just flip those vectors backward. So now the sensitivity to velocities or the becomes the input of the adjoint model, and you run it like backwards. So the adjoint circulation model actually runs backwards in time, and it gives you sensitivity to initial conditions, sensitivity to the forcing, and this is used to force the adjoint model. The cool thing about coupled model, I should say, so we did that kind of studies before without coupling, and we had to provide the covariance for the errors in this forcing, and in a coupled system it's kind of just this is just intermediate step. You don't actually have to provide the covariance for the forcing of the circulation model anymore. Everything kind of converges to the sensitivity to the bathymetry. I bring your attention to the fact that sensitivity to the bathymetry is the sum of contributions from direct contribution from the adjoint circulation model and adjoint wave model. So it's basically the sum of these two. And it was one of the kind of motivational point for me to actually attempt this exercise to see how much each of those models contribute to the correction of bathymetry, whether the structure is the same or different, and whether the magnitude is the same or different. So that's the kind of main point of this presentation, I guess. We formulate the twin experiment problem. The true bathymetry has a longshore variability in the bar shape. We use the short periodic channel. Those are small scales. It's like 250 by, the domain is 250 by 500 meters, but we run it at 2-meter resolution. So in the prior bathymetry, it's quite different from the true bathymetry. The bar is moved like 20 meters offshore, and there is almost no longshore variability in this bathymetric profile. We do allow a little bit just to be able to generate meanders in the flow. All right, so we run the true bathymetry case with sample velocities at the noise and try to simulate it in a prior bathymetry case. I don't know if you can see clearly, but our assimilation array is consists of U and V, 2 components of velocities every 10 meters in this area, covering the whole, about half of the domain. I show only the half of the domain closest to the coast. And we do a spin-up problem. We don't correct initial conditions. We start with a rest and run the circulation model for 2 hours. After 1 hour, those equilibrated waves regime kind of sets up, or even the periodic regime sets up, and you kind of can say like this meandering or unsteady behavior is quasi-stationary here. So we take velocities from there and we assimilate time averaged velocity, because we believe that it's time averaged velocities, not instantaneous velocities, that carry most information about the flow. With the adjoint method, you know pretty well what you minimize, which I like a lot. So we minimize this cost function. It has 2 terms. This is the penalty on bathymetry, this is penalty on data, and we minimize the subject to the exact model dynamics and initial conditions. So what we are looking here for, so we use a particular method for minimization called representer method. It's indirect representer method. All those methods come to running the joint and tangent linear model several times until you get the optimal solution. So the optimal solution can be written as a combination of so-called representer functions, and the method, in a few iterations, the method finds the optimal linear combination, finds those coefficients beta, essentially. And so we can represent this correction corresponding to each observation in the following way. So lambda is the result of the adjoint model, and then we smooth it with covariance. And as I told you before, lambda, the sensitivity to the bathymetry can be split as the contributions from the circulation model and the wave model. And similarly, because this is a linear statement, you can split this contribution of each observation to the correction in a contribution from the circulation model and wave model. And after you have some of these two, you kind of get the net contributions from each model. So we are going to look at all those kind of the 6 plots and see the differences in the structure for the sensitivities, corrections for one observation, and correction for their combination. Before we do that, actually, kind of as a proof of concept, the twin experiment always works. We do improve. This is a bunch of, this is 3 different cases where we improve bathymetry. We move the bar and show and kind of obtain longshore variability. This is the weakly nonlinear case, assimilating both components of velocity. Strongly nonlinear case, assimilating both components of velocity. And this weakly nonlinear case where we assimilate only longshore components of velocity, which would kind of correspond to data sets from the optical imagery. Let me skip this. Let's look at the result of the adjoint model. What does the adjoint model give you? So the component corresponding to the circulation model is shown here in the middle panel. It's kind of a singular at the observation location. There is some influence of advection along coast if you adjust the scale. On the same scale, the sensitivity to the to bathymetry coming from the wave model has this enhanced covariability along the path of the background waves. And this is easy to understand. Like if you have error in velocity here, it can be, so the joint model suggested that error can be in part because the bathymetry for offshore is incorrect. And that would affect the waves, wave propagation, dissipation, and so forth. So this, and the sum is kind of dominated by this pattern. If you apply the covariance to this now, this is how it looks like. We have this wave pattern still. In the wave component, circulation component doesn't have those. For this particular case, for this particular observation of the longshore velocity, this structure is like about 30%. Instead of kind of looking at all the data, we just skip to the sum correction. And we see that the correction to bathymetry is like negative in shore of the bar. So these 2 black lines, 2 meter bathymetry, show the prior bathymetry, show location of the bar. So negative means that we decrease depth. Positive means we increase depth. So we move the bar inshore and we increase the longshore variability. So the adjoint, it turns out that the adjoint wave model mostly works to move the bar inshore, and the adjoint circulation model moves just increases the longshore variability. So the adjoint wave model and adjoint circulation model have distinct roles in this coupled assimilation experiment. We also did experiments with different combinations of the data and look at array mode analysis. If you're curious to talk about, we can do it offline. Let me conclude. So the joint formulation, in my eyes, allows convenient formalities to explore relative contributions of different model components of a coupled system. In our case, the wave in circulation adjoint component provides distinctly different contributions to the corrections of bathymetry. Thanks.
Okay, one or two questions. I have a question. For this study, you assume your initial condition is rest. The wave is at rest, right? Yeah, in reality, if in the real model, how do you specify the condition for the wave?
Well, in practice, nearshore modeling, people always kind of assume that over a short period of time, like 1 hour or 2 hours, the wave field is steady, so they can kind of integrate the model from the rest to the steady state. If we actually try to correct both initial conditions and bathymetry, it's kind of difficult to do because correction of bathymetry affects the integrated flux in the circulation model, and it kind of corrupts the correction to initial conditions in a sense. It's a difficult exercise, so we decided not to correct initial conditions, which is pretty much what the practice is.
Okay, thank you. The last presentation for this session is given by Dr. Zupansky. She will talk about ensemble data simulation in wind industry.
Okay, this is another different presentation. It is in atmospheric science application, however, it is focused on wind industry problems. The outline of my talk will be, I will start with some general data simulation problem, then I will go into more explanation of a particular ensemble data simulation solution. Then I will point out the importance of flow-dependent information content measures, and then I will go into wind energy applications and show some results and summarize with conclusions. General data simulation problem can be defined in terms of seeking the minimum of the cost function, which is familiar to all of you, I'm sure. But what I would like to point out, we use nonlinear forecast model, numerical weather prediction model. We would like to respect the nonlinearity of this M operator, and also we fully respect the nonlinearity of the forward observation operator. A particular solution to this problem could be an ensemble data simulation one, and an example here we are using from the MLEF method. MLEF method does respect nonlinearity of the problem through change of variable and Hessian preconditioning, and also through iterative minimization. We end up with a solution in terms of analysis, XA, and in terms of analysis error covariance, PA, which is here actually a square root. So these are kind of all known facts, but I also would like to point out that not only we get flow-dependent forecast error covariance and also analysis error covariance out of the ensemble data simulation process, we also actually get flow-dependent information measures, as it was explained in this paper from 2007. Degrees of freedom for signal are flow dependent, and actually they are defined in ensemble space. Why is this important? Here is an example of ensemble data simulation in assimilating satellite observations for two synoptic cases. This is tropical cyclone Erin and also windstorm Kirill. On the first row, on the first vertical line of plots, we see observations, satellite radiances. In the middle, we see analysis error, variance in this case. And on the right-hand side, the last two plots are actually degrees of freedom for signal. And we see that there is more information. The values are higher in the areas where actually the storm is located. Or here in the lower plot, in the area where the front is located. So actually, what's happening through MEF or any ensemble data assimilation, if it's done right, we actually extract maximum information where things are happening. For example, when the storms are. So actually, we would like to know how that applies to wind energy. Sue already explained that we care a lot about wind power ramps, and I will not go into explaining what the ramps are, but actually I just want to point out that we would like to get them right, especially if we look into really short-term forecast like next couple of hours. And what we also look here is something that's called persistence ramp. That's the ramp forecasted by persistence forecast, and persistent forecast means whatever is happening in this particular moment, that will stay forever, or at least for a couple of hours. Persistent forecast doesn't mean much if you really look into long-term forecast, say 12 hours or more, then it's not really competitive to anything. But if you look into really, really short-term forecast, hour or two in advance, it's not really easy to get a better forecast. Basically, that's typically used as an industry standard upon which you want to improve. And of course, ramps are something that things are happening. Ramps are events. And in such cases, if we assimilate the data correctly, maybe we can extract maximum information in such cases, and maybe we can improve these events more than maybe other just regular events or no events. So that was kind of a question or a hypothesis of this study. So, and in order to be sure that we are doing things right, actually, we have to define some performance metrics of the forecast that we are providing. And these metrics are defined for ramps, like we have hits or we have misses in the forecast, whether we forecasted ramp or whether we didn't. And there are kind of these different categorical forecast scores, like we calculate all of them. The important ones are false alarm ratio, threat score or critical success index, or equitable threat score. Equitable threat score here is defined slightly differently compared to the standard meteorological definition. We actually use hits of persistence forecast as a way to normalize it. Actually, that plays a role like a random chance. Typically, you want to be better in equitable threat score, better than random chance. Here, we want to be better than persistence. And this theory and a lot of approximations, I call it art of approximation, then it leads to results, because we have to do approximations in order to produce results on time, and in order to produce them within a relatively small ensemble size, and also within a computer resources that are reasonable. So there is actually a lot of science here in order to be able to do this in a reasonable way. So approach here that we took was to evaluate the impact of ensemble data assimilation using a small model domain, like geographically small domain, because that's actually computationally inexpensive or less expensive. And once we see that these results are positive, then actually we examine what's happening when we increase the model domain. And in this particular case, we are looking into the differences, when we look onto the score values, we always create differences between the experiment and persistence score. So, and we did for 2 farms. First, farm number 1, we have plots on the left-hand side. This is mean absolute error reduction over a period of 6 hours due to experiment. Without EDA is green, and with EDA it's blue. And you would like to see error reduction. That means you would like to see error bars going in the negative direction and being larger. And on the right-hand side, we see these forecast ramp metrics, such as probability of detection, threat score, and equitable threat score. You would like to see these values larger, but you would like to see false alarm ratio go smaller. It would be even better if it was negative. Nevertheless, it was less positive in the EDA experiment versus no EDA. So we see generally we see positive impact of data assimilation on all measures except for the forecast horizon of 6 hours for mean absolute error. And that was, we hypothesized, because we really use a relatively small model domain, and when you use a small model domain, in later hours, the lateral boundary conditions, they start to dominate. So then we extended the experiment using a larger model domain, and we applied to the same farm and then applied to a new farm. The second farm is basically almost like independent verification. So what we see as before, we have a positive impact of data assimilation. We have a considerably larger impact in this case, and it's positive on both farm and it's positive on all measures. And it's significantly positive for the ramp metrics, and that's actually what we care about. And here is just an example how the plots look like. We have 2 ramps here. The time is on the horizontal axis, and maybe you can compare the green and red lines. Red line is a small domain, green is a large domain. You have a positive impact due to larger domain, improved actually false alarm ratio in this case, because we created a ramp that didn't exist, but it wasn't actually better than persistence for this particular ramp. But generally, the scores told us that it was better. In this case, it was better. The green line was better than persistence in general. Summary, ensemble data assimilation methods can significantly improve wind power forecast, especially the ramp forecast. These methods are, however, computationally very expensive, and we need to actually pay attention on how to reduce the cost. One idea is to actually maybe hire some software engineer experts who can do computational, who can significantly reduce computational costs. However, I didn't mention here, but the other approach would be to actually go more into reduced rank modeling or reduced order modeling, which can be computationally less expensive. However, that seems a little bit longer term research that we are still not taking on, but hopefully we will do in the long-term future. And of course, sharing experience from data assimilation at meetings like this, it's very, very helpful to us. So we will continue to monitor what's happening generally in geosciences. Thank you.
Okay, we have time for a few questions. Dushanga, I was quite surprised by your last plot. The difference between the small domain and large domain is very, the next one. It's very large than the final one before your conclusion.
The large domain.
No. This one.
Oh, yeah.
Oh, yeah. So did you verify in the same The same area?
Yeah, that was, the verification was performed, it was shown on the slide over almost over 20 days from May 2012. This is just one day from that period. Actually,
okay.
two different times from that period. But when you calculate the scores, they kind of average. Over
Okay, that explains it. Okay, any other questions? All right. Okay, then that concludes this session. Let's thank all the speakers again, and thank you all for your participation. Okay.